Hello, Applied Physics students. Here is your teaching video for the Concept Development Practice page 9.2 about the law of conservation of energy. And again, remember the law of conservation of energy states that energy can't be created or destroyed. So our energy that we have available has to stay the same. And we're going to use that to fill in the blanks for the six systems shown. So I am purposely going to save this one until the very end because in my opinion it's the toughest of the ones that are on here. So here we have, right, an object that's raised to a certain height and we see that it has 30 joules of potential energy, right? Specifically gravitational potential energy because it's raised in the air. So here we have the same ball raised to the same height. So it's going to have the same amount of potential energy, which is 30 joules. No math required to figure that out. Here, it's steps, but we're still at that same height, so this is still 30 joules of potential energy. Now, we see that it's steps to get here, right? So it's kind of taking this 30 joules and there's 3 steps. So each step requires 10 joules of energy to lift. So based on that idea, because this ball's on the second step, the potential energy here is 20 joules. And here, the kinetic energy that this ball has right before it hits the ground, again, in this case, it's not going to have any potential energy left because it's at the ground. So all of this potential energy gets transferred into kinetic energy. And so there's 30 joules of kinetic energy just before it hits the ground. All right, our skydiver here. Great, so we see up here at the top, or kind of a daredevil, I guess. Our person, though, up here at the top has 15,000 joules of potential energy and no kinetic energy because the person is not moving yet. This is all, again, stored potential energy, gravitational potential energy. So the person jumps. So here we know, they tell us that the potential energy at this height is 11,250 joules. Again, we know because of the law of conservation of energy that we have to have 15,000 joules total at each location. So how do we figure out this missing one? We're going to do the 15,000 joules that we have to have total minus the 11,250 that are kinetic or potential energy, which leaves us 3,750 joules to be kinetic energy. Here, okay, person has continued to fall, so more of that potential energy has become kinetic energy, so we should expect our kinetic energy to be a larger number, and notice our potential energy is a smaller number. Still, though, the total of these two has to be 15,000 joules. So we take 15,000 joules, we subtract the 7,500, and we get that it's 7,500 joules of kinetic energy. Here, again, we know because of the law of conservation of energy that the total of these two still has to be 15,000 joules. So we take our 15,000 joules and we subtract the 3,750 and we discover that, I think the math's wrong there, 15,000 minus 3,750 is 11,250 joules, right? So basically, notice that these numbers here, they've just switched positions, right? The kinetic energy was 3,750 joules here, and potential was 11,250. They still have to total the same amount. So now if only 3,750 joules is potential energy, 11,250 joules has to be kinetic. Here, right before they go into this tiny bucket, the potential energy is 0, which means all of that energy has to be kinetic energy, so we're at 15,000 joules. All right, taking a look at these other ones, right? Here we have an object raised in the air, and we know its potential energy is 10 to the 4th joules. And we use that weight to do some work. Remember, our work done is equal to our change in our kinetic energy. So remember, our kinetic energy up here is 0. And right here, right before it hits, all of that potential energy becomes kinetic energy. So the work done is 10 to the 4th joules. Okay, we have our inclined, inclined plane, but not with a flat plane. Okay? And again, the clue here is down here, because again, we know the law of conservation of energy says that the total of potential and kinetic energy has to stay the same every time, and it's 50 joules here. So we know that the total of these every time has to be 50 joules. That's what the law of conservation of energy says. So here, when 25 joules of that energy is potential energy, that leaves 25 joules to be kinetic energy. Here, before the ball starts to move at all, and we have 0 kinetic energy, okay, then all of the energy has to be potential energy as 50 joules. Let's take a look at this one. Again, this is that same idea, right? The total of potential and kinetic energy has to stay the same every time, so it's going to be 10 joules every time. So the total of these has to equal 10 joules, and we know 2 joules is potential, which means 8 joules has to be kinetic. Again, here, right, the total has to be 10 joules, okay? So this has to be 10 joules. And then here, they kind of are trying to trick you, right, because they didn't put numbers in. But notice, right, our potential energy is always due to energy of position. So notice that our ball is back at our same height here. So that means it's going to have 10 joules of potential energy and 0 joules of kinetic energy here. We still have to equal 10 joules. Now, the trickiest one on here is this one. And I'm going to tell you right now that you won't have something like this on a test or quiz, but I'm going to show you how to do this. Okay? So, we have a kinetic energy here and a velocity. Remember, our equation for kinetic energy is kinetic energy is 1/2 our mass times our velocity squared. So we don't know the mass of this object, but because we have both the kinetic energy and the velocity here, we can figure it out. So if I want to solve for the mass of this equation, I'm going to do that over here, right? So Ke equals 1/2 mv squared. I need to get mass by itself. So I'm going to get rid of the 2 by multiplying both sides by 2. So now I have 2 Ke equals mv squared. So now how do I get rid of the v squared? I divide both sides. So m equals 2Ke divided by v squared. So to figure out the mass of this vehicle, this is what I'm going to do. I'm going to take 2, the kinetic energy is 10 to the 6th joules. I'm going to divide that by the velocity, which is 30 kilometers per hour squared. And that should give me the mass. So 2 times 10 raised to the 6th divided by 30 squared gives me 2,222.2 repeating, okay, as my mass. So what I'm going to do is I'm going to store that in my calculator as A so that I don't have to type that in every time. So now that I've figured out the mass of this car, I can figure out its kinetic energy. Okay. So what I'm going to do here is, again, kinetic energy is 1/2 mass times velocity squared. So 0.5, the mass is the 2222.2 repeating. The velocity is 60, and I'm going to square it. So I'm going to put 0.5 times, I'm going to get my answer from A, there that is, times 60 squared. And I get 1, 2, 3, 4, 5, 6, right? So basically 4 million joules. I'm going to do the same thing here. The difference is here, instead of plugging in 60, I'm going to plug in 90. So I'll do that again. 0.5 times, again, I'm recalling my answer, and then times 90 squared. And I get 9 and 1, 2, 3, 4, 5, 6 zeros here. And again, that would be joules. Again, you won't have any like this, okay, on a test or a quiz, but that's how you can figure that out. So we've been using this idea that the amount of energy we have stays the same. It's just constantly changing between those two types of mechanical energy, potential energy, which is stored energy, and kinetic energy, which is energy of motion. So we're going to continue to use that idea back here on our second page. So the woman supports a 100 Newton load with the friction-free pulley system shown below. Fill in the spring scale readings that show how much force she must exert. Well, when she's pulling with just one rope, right, she has to pull with the same amount of force as the weight of the block, which was 100 newtons. Now, with pulleys, the mechanical advantage is equal to the number of strands that support the load or the object. So in this second case, we have 2 strands. And because that makes the mechanical advantage 2, that means it only takes half the force to lift the load. So this would be 50 newtons. Now here, this one looks like it might be 3, but there really are only 2 strands supporting the load. So the mechanical advantage here is still only 2, which means it still takes 50 newtons of force to pull up that load. So number 3, a 600 Newton block is lifted by the friction-free pulley system shown. So it's using this system here. Letter A, how many strands of rope support the 600 Newton weight? So how many are actually holding this up? There's 1, 2, 3, 4, 5, 6. Remember, this one doesn't count because it's not holding up this weight. So there are 6 strands. All right, what is the tension in each strand? Well, that's going to be equal to the weight here. So this has a mechanical advantage of 6 because there are 6 strands supporting the weight. That means it only takes 1/6 the force. So that's how we're going to figure out this tension, because it's going to take 1/6 this force. So 1/6 times 600 newtons is 100 newtons, okay? Which means that's the tension in the rope the whole time. So what is the tension in the end held by the man? It's also 100 newtons because it's the same rope. If the man pulls his end down 60 centimeters, how many centimeters will the weight rise? So this kind of goes to this idea that our input distance and our output distance are related by our mechanical advantage. Okay? So our mechanical advantage is our input distance divided by our output distance. So we know our mechanical advantage is 6 because there are 6 strands. Okay. Now, we know the input distance here is 60 centimeters. The question is, output, how far are we going to lift this up? That's our unknown, x. So, to solve for x, I'm going to multiply both sides by x. So I have 6x equals 60. And then to get x by itself, I'm going to divide both sides by 6. So x equals 10, and it would be centimeters. So how far is it going to rise? Only 10 centimeters. So the guy's going to pull the rope 60 centimeters, and he's going to raise this weight only 10 centimeters because he has 6 strands. What is the ideal mechanical advantage of the pulley system? 6 to 1, because it's the same as the number of strands that support the load or the mass in this case. If the man exerts 60 joules of work, what will be the increase of potential energy of this 600 Newton weight? Because of the law of conservation of energy, right? The change in kinetic energy is equal to our work, okay? So if he does 60 joules of work, that means there's 60 joules, of kinetic energy. So that means that there's going to be, okay, how will he increase the potential energy when it's not moving? Well, law of conservation of energy says if he does 60 joules of kinetic energy, then this object's going to have 60 more joules of potential energy. So he will increase it by 60 joules. Because all of that kinetic energy, all of that work that he does, becomes stored potential energy. And the last question, why don't balls bounce as high during the second bounce as they do in the first? So, right, according to the law of conservation of energy, right, those balls should bounce just as high as they do. However, okay, because we live in the real world, some of the kinetic energy becomes heat. Okay, so the ball actually gets a little bit warmer, or the floor gets a little bit warmer, okay, and is lost as kinetic energy. Therefore, the ball can't bounce as high. Because that kinetic energy has to become potential energy, and there's less kinetic energy, so it's going to have less potential energy after each bounce. So it can't get as high each time. So again, talked a little bit about mechanical advantage back here on the second page. The first page, remember, was all about this idea of law of conservation of energy, that energy is just kind of constantly transferring between potential and kinetic energy. However, we know in the real world where we live, on Earth, where there's friction and such, we do lose some energy. Typically, that energy is going to be lost as heat like what happens with our bouncy ball. Have a great day.